So in this class, we will analyze a problem on stress-strain relations. So in this, what he has given here is, he has given the values of the stress components at a point, and he has asked you to find the strain components. In the earlier lecture, I had explained how to find stress components by knowing strain components. So this is in the opposite way. So stresses are given, you have to find out the strains using the stress-strain relationships. So the problem runs like this. At a point in a strained material, stress components are given by, it's a triaxial stress system, that is three-dimensional stress system, whereas he has given all the six stress components, three normal stress components and three shear stress components in terms of xyz, that is coordinates. So sigma x is given as 40x square plus 6xy, 40x square plus 6xy. Sigma y is given as 60y plus 20, 60y plus 20. Sigma z is 50z square. And he has given the shear stress components, tau xy as 0, tau yz is xy cube plus yz cube plus zx cube, xy cube plus yz cube plus zx cube, and tau xz is 9xy plus 6y square z. So these are the stress components we have given. The question here is, if the value of Young's modulus is 200 dPa, that is steel. For steel it is 200 dPa and mu value is 0.25. Poisson's equal value. Find strain components at the point. Of course, he has given the point as 1, 3, 2. So he has given the values of x, y, z. So at that point, we have to find out the strain. So he has given the stress field. So this is called as stress field in terms of the Cartesian coordinates x, y, z. And at a particular point, he has given the value of x as 1, y as 3, and z as 2. We need to find the strain components. Anyway, for this, we have to use the generalized Hooke's law. Directly, we can use that. So let us write down the generalized Hooke's law equations. So generalized Hooke's law, that is the stress-strain relationships. In the earlier lecture, I have derived this. See, epsilon x. Now we know stress values, we need strain values. So LHS becomes your strain now. Epsilon x, we know that it is 1 by E into sigma x minus mu times sigma y plus sigma z. Epsilon y is 1 by E into sigma y minus mu times sigma z plus sigma x. Epsilon z is 1 by E into sigma z minus mu times sigma x plus sigma y. So one thing is during sign convention, positive values will give tensile normal stress, negative values will give compressive normal stress for sigma values, and correspondingly strains, if it is positive, it is tensile strain, negative compressive strain, like that. Anyway, here, since he has given the value, he has given in terms of x, y, z, all the three stress functions in terms of x, y, z. Since we need at a particular point, since we need the value of strains at some particular point, so we need to substitute the values of x, y, z in the given stress field. So these are the normal strains. Shear strains are given by gamma xy. Gamma xy is equal to tau xy divided by g. Because we know that shear stress divided by shear strain is g. So your gamma xy, that is shear strain, is given by shear stress divided by g. Similarly, gamma yz is tau yz by g, and gamma zx is tau zx by g. Of course, in this problem he has given only E and mu values, Young's modulus and Poisson's ratio. From that we can get the value of this g using the relation E is equal to 2g into 1 plus mu, or g is equal to E divided by 2 into 1 plus mu. Let us calculate this value. E he has given 200 GPa divided by 2 into 1 plus mu is 0.25. Now let us simplify this and get the value of rigidity modulus or shear modulus. 200 by 2 is 100. 100 divided by 1.25. So it comes down to be 80. 80 GPa is the value of G. So wherever G is there, you can put 80 GPa, the capacity. Now, since he has given a particular point here, at point in this tested material of the body 1, 3, 2, x is equal to 1, y is equal to 3, z is equal to 2. Now let us calculate the values of these stresses at that particular point by putting the values of x, y, z. So sigma x, so stress components will be now, stress components at that point will be, sigma x will be, just one substitute the values of x, y, z here. 40 into 1 square plus 6 into 1 into 3. It comes out to be 40 plus 18, which is 58. I can take this as 58. 58. Then sigma y will be 60 into y is 3 plus 20. So it is 180 plus 20, 200. Then sigma z is 50 z square, that is 50 into 2 square, so which is also 200. So these are the values of sigma by substituting the values for x, y, z. Now let us write the units later on. Now, once you get these values, so using this, you can find out the strains. So epsilon x at that point, that is 132 point, you have 1 divided by E. E is 200 GPa into sigma x is 58 minus mu is 0.25 into sigma y is 200 plus sigma z is also 200. Of course, all these values will be in GPa only. Let us take it in GPa only. Now epsilon x is this. So since all the numerator is in GPa, denominator is also in GPa, so it gets cancelled and strain has no units. Now let us simplify this. 58 minus of 0.25. So 0.25, 58 minus of 0.25 into 400, which is 100, divided by 200. So here it comes out to be minus 0.21. Minus 0.21. Since strain has no units, so it is just the value is minus 0.21. So that is the value of epsilon x. So here one thing you should keep it in mind. I have kept the value of E as in GPa only. So here this is in GPa. But this x, y, z, we don't know whether it is in meters or millimeters. So normally what we take here is, so we will take the value in MPa only. So let us take the values in MPa so that this value will be in, let me take this, then if it is MPa, then this should be 80 into 10 power 3 MPa, G value. And E value will be 200 into 10 power 3 MPa. MPa means Newton per Coulomb square. That is the standard unit for stress as well as Planck's modulus. In that case, these here I have to take 200 into 10 power 3 here. So that this becomes minus 0.21 into 10 power minus 3. So these values, let me take this in MPa. So stress values will be in MPa. So I can add that here is in MPa. Okay? In MPa, then it is understood. So minus 0.21 into 10 power minus 3, or I can write it as minus 2.1. 2.1 into 10 power minus 4. Here, negative sign indicates that it is compressive strain. That's all. Compressive strain. Next, I will find out epsilon y. Epsilon y is using this formula 1 by e. Once again, denominator remains same. 1 by 200 into 10 power 3 into sigma y. Sigma y is 200 minus mu is once again 0.25 into sigma z plus sigma x, 200 plus 50. So this is the value of epsilon y. So let me simplify this. 200 minus 0.25 multiplied by 258. So divided by I will take 2, divided by 2 I will take, so that it becomes 67.75. 67.75 into 10 power minus 5, because this is 10 power 2, 10 power minus 5. This is the value, or in other words, you can write it as 6.775 into 10 power minus 4, keeping the same power. So that is the answer. So here it is positive, that means it is tensile strain. That is hand convention. Then epsilon z, you have to put in this formula 1 by e, 1 by 200 into 10 power 3 into sigma z, it is 200, minus of mu is 0.25 into sigma x plus sigma y. So 58 plus 200. So this is the answer. So you will be getting, I think you will be getting the same answer as this only, which is 6.775 into 10 power minus 4. This is also tensile in nature. So positive value of epsilon is tensile strain, negative value of epsilon is compressive strain. That's all. Both are normal strains only. Now after this, what we have to do here is, we have to find out the shear strains also. Of course, shear strain is obtained using this formula. So gamma xy shear strains, that is tau xy by g. Tau xy by g. Now what we have to do here is, we have to get the values of tau xy, tau yz and tau zx at that point, at the same point. So at 1, 3, 2, let me get the value of tau xy. Tau xy is given as 0. At all the points there is no shear stress tau xy. Tau yz is xy cube, that is x is 1 here, y is 3 plus yz cube, that is 3 into 2 cube, plus zx cube, 2 into 1 cube. So if you simplify this, 27 plus 24, it is 51, 51 plus 2, 52, 51 plus 2, 52. So 27 plus 24, 51 plus 2, 51. 53. So tau yz is 53. Then so that is MP. It is in MPa. Then tau zx is 9xy plus 6y square z. 9 into x is 1, y is 3 plus 6 into y square, that is 3 square into z is 2. So if you simplify this, it is 27 plus 9 into 6, 54. 54 into 2, 108. 108 plus 27 is 135 MPa. So these are the values. 12 into 9, 108 plus 27, 135. Yeah. Now once you get these stress values, shear stress values, just substitute here. Tau xy is 0, therefore gamma xy is also 0. Gamma yz is tau yz by g. Tau yz at that point is 53. Divided by g is, I have to take 80 into 10 power minus 3. Sorry, 80 into 10 power 3 in MP. So both should be in same units. So let us calculate that value. So 53 divided by 80. It comes to 0.660225. 0.6625 into 10 power minus 3. So this is the shear strain gamma yz. Then gamma zx is tau zx by d. Tau zx is 135. We have calculated here, divided by 80 into 10 power 3. So which comes out to be 135 divided by 80. So which is 1.6875 into 10 power minus 3. So these shear strains also they don't have any names. Actually it will be in radians. So now here what we have to do here is gamma zx, gamma yz, gamma xy we got, epsilon x, epsilon y, epsilon z we got. Now if they ask you to write down the strain tensor at that point, I will tell you how to write the strain tensor. In the last problem, I have written the stress tensor. Strain tensor at the point 132. So it varies from point to point because the values of x, y, z they vary. Stress varies from point to point. So strain tensor is given by, at any point, is given by epsilon x, epsilon y, epsilon z along the diagonal elements. Next, gamma xy by 2 will be there here. Gamma xz by 2 will be there here. And it is symmetrical. So gamma xy by 2 will be there here. Gamma xz will be there by 2 will be there here. And here gamma yz by 2. Gamma yz by 2. Please note that gamma xy is the same as gamma yx. Gamma yz is the same as gamma zy. Gamma xz is the same as gamma zx. Now once you get these, once you write this, at this point now just go on substitute the values of the strains and you complete the strain tensor. Epsilon x is minus 2.1 into 10 power minus 4, that is the first element. Epsilon y is diagonal, this per diagonal element 6.774 into 10 power minus 4 positive. Then 6.775. Then this value is 6.775 into 10 power minus 4. So these are these epsilon x, epsilon y, epsilon z values. Now the shear strain values will be gamma xy by 2. So we have to divide these values by 2. Suppose gamma xy is 0 here, this becomes 0, this becomes 0. Gamma xz is this one, zx and xz they are same. Half of this we have to take. Be careful. 1.6875 divided by 2 we have to take. So that is the answer there. 0.84375. So I can write here 0.84375 into 10 power minus 3. Same value comes here because it is symmetrical. 84375 into 10 power minus 3. Then I have to write the value of gamma yz. So gamma yz is 0.6625. So if you take divided by 2 we have to make a 0.33125 into 10 power minus 3. So same value will come here 0.33125 1 to 5 to the power minus 3. So this is the strain tensor at that point. Once you get all the 6 strain components, strain tensor is written in that fashion. So given the strains, how to find stresses? Given the stresses, how to find strains? Both the problems I had explained. So using generalized Hooke's law or Lamy's equations, you can find out by knowing the stress strain relationship, you can find out stress by knowing strain or vice versa.